Hi there, this is Mr. Sand, and I'm going to be talking to you right now about the types of radiation, alpha, beta, gamma radiation. So let's just kind of review here. We've got a nucleus. Inside a nucleus, we've got protons and neutrons. So let's just say that this is an atom right here, and I'm going to shade in some of these guys over here. All right, let's put a couple more. Let's see, 1, 2, 3, 4, 5. Let's do another one, 6. So this is a nucleus with 6 protons. I'll make those dark ones be protons. Those are protons. And these right here are neutrons. Right. Now I'm going to make, what am I going to make? I'm going to make some electrons around here. So in a stable carbon, this is carbon because there's 6 protons. There's, looks like 6 neutrons as well. So this is carbon 12. So in this atom right here, there's going to be electrons. Let's call this an electron right here and an electron right here on its first shell. Yep. And then there's going to be an electron here. Let's put another one here. Let's put another one here. Let's put another one here. And there's 6 total electrons in this atom. Right. Okay. Now we're going to use this to describe radioactivity. Radioactivity is any time that something comes out of a nucleus of another atom. So that can be energy, that can be mass. So coming out of the nucleus, that's this region right here in the middle. That's what defines something as radioactivity. So there's 3 types of radioactivity. The first type we're going to talk about now is alpha. So let's just imagine here that out of this nucleus, boop, comes an alpha particle. This is one type of radiation. This is massive. Pow, it's massive. The alpha particle, really what it is it's a helium atom. It's a positively 2 charged, I'll just put the positive 2 charge right here, helium nuclei. So it's 2 protons and 2 neutrons just shot out of the nucleus. So it's massive, but it doesn't penetrate things like smoke or air for very long. It's very massive. It gets stopped very easily. So it's stopped easily. So things like paper, air, they can stop it. Paper, air, clothing will stop it. Okay, so that's one type of particle, an alpha particle. We're going to say that that's relatively low energy as well. Okay, so it's low energy, it's massive, it's just a helium nuclei, there's no electrons around it, it's just 2 protons and 2 neutrons being shot out. That is an alpha particle. It can be stopped by paper or air, whatever. In fact, it's used in smoke detectors. The way it's used in smoke detectors is that we've got this alpha source. This is a quick aside here. So let's just imagine this is a little source of alpha particles. There's tons and tons and tons of atoms shooting out alpha particles. Pew, 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 pew. And there's a little detector over here. And it normally is just streaming out, and this detector is collecting that alpha particle and set up through a circuit so that once it receives that alpha particles, everything's good. There's no need for alarm. But then if smoke comes through here, disrupting this, it will block the alpha particles, and this will not detect any more alpha particles. Oh my God, that trips the circuit, and it makes an alarm. That's a smoke detector right there for you. They use a specific type of alpha particle smoke detector. Right now we're going to go on to beta. Beta. I'm going to use teal color for this. So that came out of the nucleus. Now, beta can also come out of the nucleus. This is an electron coming out of the nucleus. It's called a beta particle. There are 2 types of beta particles, but we're only going to consider one. It's the electron. It's this negatively charged particle here. Okay, so it's a negative. It's an electron. It is it is stopped by stuff like aluminum. They always say aluminum. I'm not sure why. Nothing else is ever said about this. But aluminum, it's stopped by, so it can go through paper and air, but it's stopped by aluminum. So in the kind of like relative energy, this would be called medium energy. We're not even going to give value to this. It's just energy. It's somewhat energetic, but not as energetic as the next one, which we're going to call gamma. So gamma is also shot out of here. So gamma, it's not really right to call it a particle, so I'm going to call it a gamma ray. What? Gamma ray. And there is no symbol besides gamma. We can put 00 there if it makes us feel nice. It helps us sleep at night. But it's very high energy relative to the others. And it's stopped by lead. So stopped by lead. We keep these in lead cases. They're very energetic. They can go through aluminum. They can go through air. They cannot go through lead all that easily. You're going to have some thick lead as well to stop all the gamma ray particles being shot out of an atom. This is a radioactive atom, meaning that its stuff is being shot out of its nucleus. You can shoot an alpha particle, you can shoot a beta particle, you can shoot a gamma particle. And the reason why they shoot these things out is because they want this atom is going to be more stable if it's shot out. That's all the discussion we're going to be talking about it. And that's the limit of our detail that we're going to go into. It's going to be more stable if it's shot out. So this atom that I just randomly picked here is not typically a radioactive atom, but it does decay. It radioactively decays, and then we call that carbon. We can actually determine the date of how old an atom is based on how many particles have come out of a sample of bunches of carbon atoms. But anyway, that's just an aside. These are the different types of radioactive decay. There's alpha, beta, and gamma. Low, medium, and high energy. They're stopped easily, stopped by some stuff that takes some stopping, and this is stopped only by lead. Now, these little symbols that I've drawn over here are important because, I'll tell you why. Because if you're given a problem, this is the first time we're actually given equations, chemical equations, so I'm going to use a different color. I'm going to use plum. So let's say, I don't know, you've got this element right here, uranium 238. And this uranium is going to shoot out a particle. Let's say it shoots out an alpha particle. So if it shoots out an alpha particle, we'll say that this is the alpha particle. That's how you write alpha. This is a simple alpha. That's the alpha particle. But what's going to be remaining? What is the remaining element here? Well, the way you figure this out is fairly simple. You take a look. This is the atomic number down here. And you say, okay, well, on this side of this chemical reaction, we've got 92 as our total number of protons. Over here, we need to add this side up to equal 92 as well because the mass hasn't changed. Overall, we haven't lost any mass. And the same thing's true up here. This number up here, this is the mass number. This is 238 on this side of the arrow, so it needs to be 238 added up on this side of the arrow as well. So over here, we can deduce what this element's going to be and what its mass number is going to be. So if this is 92 over here and this is 2 right here, this must be 90. And we can look this up in the periodic table. What is element number 90? Well, if I check my periodic table, I see it's I see it's thorium. TH. Thorium. And now what's its mass number? Well, this on this side is 238. Over here, they've got 4. So to get back up to 238, we need to have this be 234. So in a way what we can do is we can see that this On this side, it will equal, because this is the reaction here, this will equal both of these elements added together. Same thing on the bottom. 92 equals 2 plus 90. 238 equals 4 plus 234. These are ways in which you can reason out what this final element's going to be. It gets a little bit tricky when we're talking about beta particles because beta particles are weird. So let's do a beta particle example. Let's use uranium-238 again and set it up with a beta particle decay. So I'm just going to put it right over here. 238, uranium, 92, it decays, and it's going to spit out a beta particle. That's a beta particle right there. This is a beta particle. Or we say beta. If you're British, you say beta. I just learned today. Okay. So what is this going to be over here? That's the question. What is it going to be? Well, we have 92 on this side, and then we have minus 1. Huh? Minus 1, right? What does this have to be? Oh, I'll use a different color here. Let's use tin. Okay. This has to be 93. Weird. And if it's 93, you can look this up in the periodic table. 93 is Neptunium. NB. Neptunium. And over here, 238 equals 0 plus, it's got to be 238. So this will be our answer over here. A little terminology here. This right here, this is called the parent element. These over here are called daughter elements. And if it's not an element, like in this case, this electron is not an element, you can call this a beta particle, and this just would be the only daughter element remaining. So it's the stuff that's left over. I don't know why it's daughter, not son. It's just the way it goes. Okay? So that should help you with all of these problems. You could probably do a more complicated problem where you have several of these elements kind of on one side and several on this side. You add all the numbers up. They have to equal the same number on both sides of this equation. That's in short how you do any of these kinds of alpha, beta, gamma equations. And yeah, have fun.